Okay, so the deal here is when we have these quantities, we can associate them with a number, but it's not just a number. It's a number with a dimension or a unit that indicates what's the yardstick used to measure that, and what sort of thing is it. Okay, so x, we might have a variable x in our model, or in our program, in our agent-based model, or in our Venn model. And this might have a quantity of 1, but it's further labeled as being dollars per foot, or dollar per person. Maybe this is the number of dollars required for a test for chlamydia for this person. $1 per person is the cost of the test. We could have that, right? Here, suppose it's dollars per foot. We could convert this to meters, right? So if we wanted to convert a dollars per foot to a dollars per meter, we could multiply by the number of feet per meter, right? So if we had something we know it costs dollars per foot, we want to ask, okay, how many dollars does it take to, per meter now? We just multiply it by how many feet there are in a meter, right? Does that make sense? Yeah, okay. Now, if we had some other measurements, like dollars per foot squared, suppose we had a model of apartment pricing, real estate pricing, right? House pricing or what have you, for commercial real estate, maybe it's office space. We have dollars per, and we want to convert squared, per square foot. And we want to convert that into dollars per square meter. We would multiply it, but we wouldn't multiply it by feet per meter. We'd multiply it by feet per meter squared. Right? So if this costs $1 per square foot, and we want to ask, well, okay, I'm used to thinking in square meters. How much is that per square meter? I wouldn't just multiply by 3.208, which is the number of feet per meter. Instead, I have to multiply times that squared because of this square here, of the fact that this is dollars per length squared. So what I'm saying here is that the exponent for this dimensions, the fact that there's a squared here, means when we convert from one dimension to another, we want to convert to meters squared, because this is the dimension of this is cost per length squared. When we convert it to a different unit of length, here meters, we have to multiply times that coefficient to the squared power. Does that make sense? Okay. Now, this is the thing which gets pretty deep. I mean, I think we're all comfortable with this. We've all hopefully done these conversions before in our lives at one point or another. We're reasoning about square footage. And we want to rent something for a small company. And we ask, okay, well, what is it per square meter? Because we have our needs in square meters. And so we can convert it in the appropriate way. Right? Or if you're calculating the area of a pizza, and you know how much, how much you can eat in square meters of pizza, you might convert it and, accordingly. I mean, it's a 9-inch pizza, and so you might figure out, okay, is that enough for 2 people or 1 person? Okay, but this is getting closer to the heart of the matter for some of our work, okay? The dimensions of a quantity do not depend on a given dimension. In other words, we may have in our model dimensions of length, of time, of person, and of dollar. And if a given quantity only depends on, say, dollars in feet, if I were to write this out, if this is dollars per foot, I could write out its dimension as cost to the 1 power, length to the -1 power, -1 because it's dollars per foot. The foot is on the denominator. And I could, what would its exponent be for time? What's the exponent of that for time? If this were dollar per square foot per year, or per month, let's say, for real estate, what would be the dimension for time? The dimension. It would be help me think these things through. Dollar per square foot per month. That's what you might pay to rent an office space in Innovation Place, right? Dollar per square foot per month. What's the dimension? What's the exponent associated with the time dimension? We could represent this. We could write this as dollar over foot times month, right? It's dollar per square foot per month, and so we could rewrite it as dollar per foot times month. What's the exponent associated with time? What would be the exponent associated with time for that?
-1.
No, -1. It'd be -1. Because time is in the denominator here to the 1 power. We don't write it as to the month 1, but it would be -1. Okay, so if we had dollar per foot per month, it would be that. So how if I just have dollar per foot? What's the dimension associated with that? We again have cost to the 1, length to the -1, because foot is a unit of length. And what do we have for time? Is it time to the 1? Is it time to the -1? Well, folks, we write it as time to the 0. What's the value of a given quantity x, a non-zero quantity x to the 0th power? It's what? 1. So, in short, it's saying it doesn't depend on time. There's no dependence on time. Does that make sense? No dependence on time at all for this?
Why would we bother writing in time and all that? I can think of 3 million different variables and units we could add in there, but there's no sense in tapping.
There is a sense. There's a big sense. So, for a given problem, we decide on the units that are or the dimensions that are relevant. And we're going to have to use that in a big way in coming slides. So we're going to have to delineate for our model, what are the relevant dimensions? And that's why I was saying earlier, suppose our model had person, time, dollars, and cost, and say length. Right? Now we have 4 dimensions. And this is what I was saying earlier that I glossed over. We can choose our dimensional system. And for this model, those are the 4 that matter. Now, we could write out all the others, but it turns out that's not going to be useful, okay? If our quantities don't refer to them, if they don't depend on them in any way, it's not going to be a useful exercise. We could do it. It's not going to hurt, except it's going to waste our time. But if our quantities are actually with respect to these dimensions, if some quantities are, dollars per person, and others are dollars per meter, time. Others are person per meter squared or something like that for density of people in an area. We will want to use those dimensions in writing this up, okay? Those dimensions which are relevant to our model. So what I'm saying here is that dollars per foot, because it doesn't mention time, it doesn't depend on our unit of time. It's invariant to what our choice of time is. We can write it out in this form. Cost to the 1 power, length to the -1 power, time to the 0th power. Does that make sense? Okay, now let's complete the circle here, folks. So up here I said, if you are converting between units, if you're converting between units, that the conversion constant you use depends on the units the power associated with the unit conversion. So if I have something like this, dollars per foot, and I want to convert it to dollars per meter, because I'm shopping for lumber or something, or maybe I'm talking about the dollars to build a subway, then I have to multiply it times number of feet per meter. But if I'm dealing with dollars per foot squared, I have to multiply it times feet per meter's quantity squared, which is 10.7864. So suppose we have something that has its power. Suppose we have dollars per foot, and I decide to convert time. I want to measure time in years rather than in days. And I have a dollars per foot quantity in my model. What do I have to multiply that by to convert time in that way? Well, I'm saying what you have to multiply it by depends on the power associated with the thing. So for this calculation, what I had to multiply by was 1 foot per meter, precisely because this is 1 foot to the 1 power. So I'll just make this very explicit, like that. This is per foot square power, so I'm multiplying times that there. So, folks, what do I need to multiply by if I have this to the power of 0? 1. In other words, it doesn't depend on it, so it's multiplied by 1. If I have dollars per foot, and I decide, if I have something at dollars per foot, and I decide I want to measure time, instead of in seconds, I want to measure it in years. Multiply it times that conversion constant, second per year, to 0th power, which is 1. So it doesn't change, in other words, right? When I convert in this way units, it doesn't change because it's to the 0th power. So it doesn't change. Okay? So look, we can express a board's length in our model, if we wanted to, as length times time to the 0th power. And that's basically saying it doesn't depend on time. So we want to convert time from milliseconds to microseconds, or milliseconds to centuries. It's not going to change the board's length. Not going to change at all. But if we want to convert meters to feet, then that will change length in a linear sort of way.